All right. Well, I'll go ahead and kick this off. It's 1:01, and I got some fun stuff to go through that I wanted to mention, and I'm sure people will trickle in and hopefully they can catch up from there. But yeah, welcome guys to this talk on MLOps, and we're going to focus on kind of the general concept of what MLOps is, but we're also going to dive into some more specific stuff on how to operationalize ML.NET models, so put them into production, how to track all the metrics they have, and how to really get like a modern pipeline for AI in terms of ML in .NET. I'm not expecting any backgrounds in machine learning for you all, or necessarily in MLOps for this talk, so I'm going to try to keep it very general. We're not going to dive into machine learning per se so much, but we're going to talk more about the processes and techniques and challenges that you may face as a data scientist or a machine learning engineer to get things in production. And I've tried to gear this talk a lot against both software engineers with or without previous experience with machine learning, as well as data scientists trying to get into the field. So to kick things off here, quickly about myself here. My name is Alexander Slotte. I am based out of Washington, D.C., so not very far away from where you all are at right now. I'm a Microsoft MVP in developer technologies, and on my day job, I spend all my day developing web apps in .NET Core, and I actually gave a talk yesterday on my migration from .NET Framework to .NET Core during last year. But on the side here, I love ML.NET, and I spend all my time mostly promoting the library, talking about it. I founded a conference regarding ML.NET with some other folks last year, and I also do some open source tools for the community. So for example, MLOps.NET is a tool that I've written with some other people around the world, and we will definitely dive into that a bit later as well. If you at any point would like to kind of have an assessment of how to bring MLOps to your organization, if that's something you want to do, whether that is in C# or if that is Python based or scikit-learn and so forth, or if you just want to have an kind of assessment of how you can sprinkle some more machine learning into your apps, definitely let me know. You can contact me at alexander.slotte@excel.com, or you can find me on Twitter, whatever works best for you. All right, so we're going to talk about MLOps today, and yes, it is a thing. And I think all of you kind of can understand, in theory at least, what it's all about. Of course, it branches off from DevOps, and it's kind of just merging DevOps and machine learning together. And it's all about getting that continuous delivery and that culture in your organization of getting incremental deployments to production and having a better understanding of where your model's at and how it is actually behaving in various environments that we, for many, many years, haven't really had in the machine learning and data science community overall. MLOps is very, very new, and we'll dive into the details and see kind of how it's evolved over the years as part of this presentation. Let me bring up the messages here as well. So if you have any questions throughout the talk, don't hesitate to raise your arm or send a message, and I will try to monitor the chat here. So I will kind of stop and answer a question. So first off here, there are a couple of resources I wanted to be aware of if you want to read more about this later. Martin Fowler has written an amazing article that kind of prompted me to give this talk for the first time last year, and it's called C for ML, or Continuous Delivery for Machine Learning. So I definitely recommend you go into his article and read that. It's together with ThoughtWorks, and he's really going into depth there on like some challenges and things that you need to think about. Google's also a thought leader in this space. I recommend a research paper that they have published called Hidden Technical Depth in Machine Learning Systems, which really focuses on this specific area and teaches you a lot about what to be aware of and what to think about here. And also, of course, Microsoft, as always, is a thought leader as well, and they have a more general approach. Azure ML as a service is kind of all about MLOps, to be honest. And that's kind of their premier service that they are pushing, but they also, of course, have other materials for this. But to start things off with, I am a big Star Trek fan. I don't know how many have watched Star Trek Discovery lately, but of course, the original Star Trek and Star Trek Enterprise and so forth is kind of on people's minds. But I want to take a step back here and look at the perspective from a data scientist and Commander Data here is going to be our test subject here to kind of understand his day-to-day activities and how we get a machine learning model from user data to production on a very high-level scale, just to understand what steps he's taking and what challenges he's facing of getting that consistent delivery and consistent quality. And then we'll look at what we can do differently to make that even better, of course. So we start off with the general process here. Kind of depending on, of course, what your model is going to do and your use case and your organization, this may look different. But in general, there are 3 steps that you want to follow, or a couple steps you want to follow when it comes to creating a model. Data preparation, model training, model evaluation, and eventually some kind of deployment to production. So your model can be made available either as part of application or as part of a Kubernetes container or something like that that could be consumed from another application, right? So what would a data scientist start off by doing here when he's trying to create a model? Well, maybe he would like to collect some data first. So you need to find good data for his model, and you need to understand how it looks and what shapes it has. So in our data scientist case here, he may start finding some internal CSV files. So maybe he wants to create a machine learning model to understand sales of a specific product better. And he happens to have, CSV files on internal hard drives available for him to look at and assess. So he may look at some, mapped drives and just find data there that they can use. He may then convert some of the values in those data sets because they don't make many sense for him maybe. So he maybe want to clean up some columns. He may remove some empty values, some null values. He may remove columns as a whole, or he may add, computed columns for his specific use case. But during this whole process, he is maybe not writing down really where the original data came from. He maybe not noting down how he made those transformations. And this data as well, there's no history of it. So we don't really know who's changed it before or where it originates from. But that's just the way our data scientist is currently working. He may then move on to model training and look at things like the algorithm and the hyperparameters and cluster management. So this is all about training a model based on the data he has. So he now is trying to train a model to predict sales of, let's say, a product in the company. So he's feeding this algorithm that he's choosing a lot of data. But he's sitting here on his own computer, offline from the world, and he's trying an algorithm A, and then number B, and then C, and so forth, until he finds a model that he thinks is good. But he may not, again, not note down which ones he's tried. He may not note down which hyperparameters he have trained or used. And when he actually wants to deploy this for training, he may just compile the code, or not even compile it, just copy it over to the cluster itself, and then let the cluster kick off the training by itself. And this may all be just a manual process for all it's worth. But it works really well for him. And to find out which model is good, he may, of course, evaluate the model and understand some metrics like the F1 score or the accuracy, which is most commonly used, right? So it's 95% accurate, and that's great. And you may also check the performance to make sure the performance of the model is as expected. But again, he doesn't note this down anywhere. It may end up in a Word document or an Excel file somewhere on a shared drive, potentially, saying, hey, a model with that was created on this date has this accuracy. That may be sufficient for him, but that may be kind of all he does here. And at the end here, he may deploy the model or copy it over manually to some kind of model repository. That could, for example, be, again, a shared drive internally, or it could be a blob storage, or it could be somewhere, because he's done. He has created a machine learning model of his liking, and he's deployed it to some kind of repository. And from here, the development team or the ops team will take over, and they will try to incorporate this into the application, or they will try to deploy it to Docker container so they can consume it. But the data scientist's job here is done, right? So what do we notice from this segment here? What are some thoughts here? Well, the first one, of course, and things that I'm kind of overly highlighting here, is that everything is manual. Manual execution of every step. It's very difficult to repeat because it works on his machine. And we all kind of know that concept, right? It's not something we want and something we struggle with for many years in the software engineering community. And it's very siloed, and it focuses mostly on model training. The releases is, if anything, not even frequent whatsoever. It's probably very ad hoc. Whenever he feels like training this model, maybe they do it one time, and maybe after that, he will kind of give it up. And there's definitely a lack of auditability. There's no audit trace here from like the model that goes to production all the way back to what data was used, what hyperparameters was used, the algorithms. So if someone comes back and say, hey, this model was crap and it caused this and this damage, and we want to sue you right now, can you tell me how you trained this to at least make sure that you have done your due diligence as well? And this is very important, right? If you look at federal work, or even something like a machine learning model trying to do automatic interviews with people, if that model is biased and says this person, I will not hire that person because of this and this criteria, you need to be able to audit that model to make sure you can prove that it's an unbiased model and not bias a certain demographic. So that's very important. And if you don't have that auditability because of a very manual step, then you will lose that, and you probably will also lose a lot of money in lawsuits. So this kind of maturity level is called maturity level 0, where everything is manual. You're very exploratory when it comes to data science. You are just trying to figure out how to do it for your company. You don't really care so much about the process. You just want a model. You want something out in production. And that's fine. A lot of companies start at this level. It's very normal. It's nothing to be thrown upon by any means. And it's a great way to get started. But as we move further and further into making ML and AI more mainstream, we also need to kind of dial up the level of automation and level of reliability that we have in our processes. Like no one, well, very few at least, I won't say no one, but very few today would be acceptant of a software application being built locally on a computer and then copied over to production, right, with the DLLs. We wouldn't really approve of that. We would not approve of having no source control, right? We need source control. Otherwise, we can't revert changes. So it's very important that we keep those things in check. And the same thing with machine learning models. We need to kind of get there. So throughout this presentation, I want to walk through kind of how we get further down to maturity level 2. And then I want to show you some demos as well on how we can do this in C#. So, but one thing I wanted you to take away well from this presentation is that building machine learning prototypes is pretty easy, right? Well, I wouldn't say it's easy, but once you start doing it, it's pretty repetitive, and putting in production is not very hard. We got a lot of help with the cloud services that are available, and we also have a lot of auto ML features that we can use. But deploying it to production repeatedly and with good quality and auditability is very hard. And the reason for that is basically because a machine learning system or a model is a lot more than just the code itself that trains the model. So the black box here kind of represents the part we actually train the model. And then we have tons of other stuff to think about here. For example, data collection is a huge thing. And we talk about DevOps then, making sure we have our data pipelines clean and proper and great, Data verification, making sure the data is sound and doesn't have strange values or other stuff here, right? The whole infrastructure serving of our cluster, if you're doing deployment through Docker container, that's a whole new thing as well. And making sure that's configured properly and making sure your machine learning models are monitored in production is really important. So we have to just make sure that we don't underestimate the burden of all these things. And as Google put it in their paper as well, is that all of this stuff here that we don't think about, that's hidden technical depth. And if you let that kind of grow over the years, it's going to be very difficult to deal with later. So you need to make sure you're on top of this and make sure you do something about it. So in general, after this introduction here, what MLOps is trying to do here, it is trying to address model reproducibility and versioning. Is make sure that we have auditability and explainability. We have to figure out how to package a model and do some validations, and we have to figure out how to deploy it to production or another system, and make sure we monitor it once we have deployed it. So these are kind of the 4 bullet points that MLOps is trying to do. And regardless of what we're talking about in terms of details here. And currently in more experimental organizations, we don't really have any of this in place by itself. All right, so how do we get there, right? Well, to think about how to get there, let's take a step back and think about what is different between MLOps and DevOps. Why are they different and how do they different? So in general, what is different between software engineering and machine learning engineering or data science? Well, first of all, when you look at a team of software engineers or DevOps in general, you tend to have people that do have some experience with production grade systems. So putting things to production, we have some experience in, doing the ops in general. Automation is definitely a large thing that software engineers are good at in general. I'm not to say that data scientists can't be good at these things, but generally they come from a more research background and they are not necessarily as fluent in system management and operationalizations. So the team skills in a team that tries to bring machine learning models to production may just be a little bit different. So we have to be aware of that and make sure we kind of build that up as well as needed. The development cycle is also very different. Machine learning models is very experimental in nature. We try things, we don't really know the answer. We can't really plan in the same way as we do with software engineering. We can't say, I want a new page. The page should have a left menu and should this and this and this. We actually don't know in data science if a model is going to work at all, or if we ever will even get a model. So it's a lot more experimental, and we need to make sure we have a process that supports that. If we look at testing, automated testing is super important in software engineering, and we can do that on multiple levels. But when it comes to data science, it is a lot more difficult and complex because you're not necessarily testing, input gave this output, because the outputs are non-deterministic. So you need to think about how do you test a model and how do you test your data. Fourthly here as well as deployments. They are much more complex because usually when you talk about deploying a machine learning model, they can be either integrated into the system or they can be self-sustained in a Docker container. But regardless of the solution you do it, there's always the case that someone is consuming your model for their predictions. You need to make sure that the schema hasn't changed for those predictions, both for return and input schema, as well as how a change in behavior of your model may actually affect the application that calls you. And then the last point here I want to make people aware of that we'll dive into a bit more later is production monitoring. When we talk about monitoring in production for a software application, we usually just think about logs and making sure we have uptime. But that's not enough when it comes to machine learning models. We also need to make sure that they don't, the prediction hasn't changed. So if the environment around it changes, the prediction they will give will also change. And that can actually lead to a model that is slowly deteriorating over time and causing incorrect decisions. And we'll look into that in just a few slides. So with all that said, though, can't we just build a CI/CD pipeline for models and kind of be on with it? We could, for sure. Let's see if this video plays. I don't think so. I was supposed to show the dark forces here, but we'll skip that. We could definitely build a CI/CD pipeline, but we can only do that if we understand what we're trying to react to here. So, at some point here, we want our model to run through our CD pipeline based on changes. If you look at the software engineering application, right, we usually trigger a new build and maybe even deployment to production if we have change in code. But when it comes to a model, we have many more axes of change. Things can change in many more dimensions. And the first thing that can change, of course, is data. So if we suddenly get a new data set for training and validation for any reason, we will get a new model and we need to change because of that. If our code changes, either our machine learning training pipelines or the consuming application, that should also be warranted a new training round. And finally, if anything as part of the model changes, we also need to do a new trigger here. So let's dive into each of these and understand what can change specifically that we want to automate and create a pipeline for. The first thing here is the data, of course, and that's kind of intuitive if you think about what machine learning models really are, right? They're basically an algorithm that is fitted around a specific data set. So if that data changes, then your parameters for your models will also change, which is pretty expected. So things that can happen, right, is we can have a new or removed features. So that means that we can have new columns in our data sets. Maybe we are measuring weather, and suddenly we're predicting weather, and suddenly in our data set we've also added a temperature sensor from another city in the US, and that could be helpful for predicting movements of clouds. I don't know, for example. But that, for example, is a new schema, and the schema is going to cause the model to change. So we need to retrain. Distribution and cardinality is a very common thing to cause retraining. So with that, I mean categorical cardinality. Let's say we have a fraud classifier. It's trying to predict if we have fraudulent transactions in our credit cards. And previously, we had about 30% of our data sets being fraudulent cases and the rest being non-fraudulent. So we have like a 70-30 split in our training sets. That's what's used for training our data on. But we suddenly get more information about fraudulent cases. So we have like 50-50 now. And that will definitely change the model's behavior, and it will have much more to learn from, and it will create a much more equal model. So that's definitely also a time where you want to retrain your model based on that. And then lastly here as well is sampling. So if we suddenly change the frequency of our data collection, that's also going to cause the need to retrain our model. Let's say, for example, that we again go back to our weather example. We are measuring the wind strength every hour, but suddenly we start checking the wind strength every minute. That sampling frequency change will also be a reason for retraining. If you look at the code stuff later, when I talk about code things in general, I mostly think about things like new business needs or features in the consuming application. So let's say we have an application that classifies people and images, but suddenly we also want to identify where they are. So not only do you want to like say this is Brad Pitt or Julia Roberts, we also want to find where they are in the picture. That's a new business requirement, and most likely we'll need another model or a tuning of the model to do both classification and segmentation. So that will also cause the model to be retrained. Maybe we have bug fixes. Maybe our transformations of data in our training pipelines is incorrect. So we need to change that. Or maybe we will have some change in our consuming application that will also need to cause a retraining. And lastly, a very common one is configuration-based changes. This is mostly the case when you have you want to make sure things are performant. So you may have a GPU cluster that you use to do predictions with your model, and suddenly you reduce the amount of resources you have available for your predictions. Let's say you take away one GPU, or you reduce the GPU you're using, right? So in this case here, your predictions may be slower. They may not be up to par what you're expecting. So you may want to retrain your model to find a more optimal model that can be faster. So that can be performance-based. And the same thing when it comes to changing the container image configurations as well, that will affect the performance in a way or another. And the last thing here I can change is the model itself, and that's kind of obvious. But there's a couple of things that can cause it to change, and the most common one is just general research experimental. So, for example, we could have picked a new algorithm. We can go from decision trees to support vector machines or something like that. Or we could just fine-tune hyperparameters. Let's say you have a deep learning model and you are using 50 or like 5 epochs to train your neural networks, but you then decide to use 12 instead. Because you think that that's going to be a more optimal result. That definitely can cause a retrain. New data, of course, will cause the model to change, but the important one here is dependencies. So you, of course, use all kinds of open source software when you train models like NumPy and Pandas, TensorFlow, and PyTorch and scikit-learn. If you change that dependency version, that can definitely cause the model to change. We've actually seen that with scikit-learn that there was a major bug in not too long ago in scikit-learn that caused the classifications to be very different than what it should have been. And when they updated scikit-learn, you will get a more accurate model if you use the new version. So making sure you track what dependency you're on and what version is very important, and you do something about it when you change it. So, as you see here, there are many axes of change, and you need a solid way of tracking them and working with them. But if we move on here to the testing segment, and before I start here, I want to just kind of open the floor up a little bit and see if there's any questions so far on what I've gone through, or if it's clear enough. All right. If not, I will also have questions at the end. So if you have anything, you can save it to then. But let's look at testing, because I think this is a very fascinating area of machine learning and MLOps in general. We have mostly two types of testing when it comes to machine learning models. And the two ones I want to talk about are data validations and model validations. So data validations is, of course, making sure that your incoming data that you use for your training is accurate. So maybe you have you want to make sure that your values in a certain column is within a certain range. You want to make sure that there are no null values and transformations are working as expected. And for your model, you want to make sure that the model you currently are deploying or just trained, is it better than the one I have in production? And what is the bias and what is the fairness? Because you have to remember here, if the model we train for any reason whatsoever is not better than what you have in production, there's no reason to continue with it. It's not like we're going to retrain our model on new sort of data and then just deploy it to production and say, hey, this is better. We're just going to do it. It has to be a reason, and it has to be better than what we have in production. And that's something we have to be cognizant about. And the best way to explain it, I think, is to look at a diagram for testing. And this is straight out of Martin Fowler's article for CD4ML that I recommend you to read. And if you're a software engineer, I think you can recognize a lot from just general engineering. You see, like at the top here, you have exploratory tests, and then the further down the chain you go to more low-level tests. So you go to end-to-end test, integration test, and then at the end, you end up with unit test here at the bottom right corner. But if you look at this triangle, it has much more to it than just the pure software engineering testing. It has things like model bias and fairness, the performance of the model, checking the data pipelines, validations, as well as checking the model itself. So what I want you to take away from this specific illustration is that when you test a machine learning model, either alone or as part of a system, there's a lot more to take into consideration. And you need to really make sure you test all these things, especially focus on things like explainable AI and model bias and fairness, because that's something that will be more and more common as we move forward. And there's great tools doing this, so it's not like you're going to have to reinvent the wheel by any means. It's just you have to think about it, and you have to also plan for it. All right, so moving on here to production monitoring. So again, if you deploy a software engineering app to production in a container, in a system, and leave it like that, it's not going to deteriorate. It's going to stay the same, given that you've updated your servers, make sure they are healthy, right? It's not going to stop working. It's going to behave the same way as always done. But if you deploy a machine learning model to production, it's going to deteriorate over time. And the way I like to think about this is think about a machine learning model that predicts weather. And let's say we developed that model in the 1920. And let's say we use that same model to predict the weather for tomorrow. If you do that, that model is going to be very, very wrong based on the fact that we have climate change and things have warmed up and things have changed around us in the climate that we just didn't know about in the 1920s. That's called the environment slowly changing, or it's calling a data drift by itself here. And there's different kind of data drifts. There are structural and semantic and also infrastructure drift. But the thing to think about here is that a model is only relevant based on the data it's been trained on. And if the data has changed for any kind of reason, which it does in just real life, we also have to make sure our model is retrained and repurposed. Just like us human beings, we learn to adjust our assumptions and we learn to adjust our decisions based on a changing environment, we also need to have that retraining phase of a data machine learning model in production. Other things to think about here as well is things like model input and outputs. So let's say you have a machine learning model that is a recommendation system for an e-commerce site, and it's going to recommend a certain kind of product for a certain client that serves the web. And suddenly you introduce a new product to your product catalog. Maybe you start selling, I don't know, peanut butter for some reason, and you've never done that before. If your machine learning model doesn't know that there's peanut butter as a category it can recommend, and it doesn't know anything about who likes peanut butter or why it would like peanut butter, it will never recommend that because it's just not aware of it. So we need to train the model to understand that, hey, there's actually something over here that you should know about. And it's the same thing, think about a human. Think about a service staff at a warehouse or at the mall, right? They are going to recommend things for the clients and customer come in there that they are aware of. They will not recommend something that they have never heard of because they just don't know about it. So the models are exactly the same. And also when it comes to model inputs here, if suddenly the schema changes or the number of options changes, that will also cause a retraining to occur. So again, production monitoring is very important. Please don't miss that when you start talking about machine learning systems and models. It is very important, and it will be very, very helpful for you going forward. All right, so that was basically the theory of MLOps. And now I want to switch gear a bit and look at tools and tooling itself for a couple of minutes. And then I want to switch over to a demo instead and look at how we can deploy an ML.NET model to a Kubernetes cluster. And hopefully that is helpful for you all. So based on kind of the theory here, what do we need in a tool for us to be successful? What kind of support do we need to do this? Well, first of all, we need a way to discover and access data readily. And we need especially some way of tracking a model lifecycle. So we need to track the data that's used, we need to track the metrics that came out of it and the results, and anything else that can be useful to determine how a model was created. We need version controls. So we need some way of storing models, and we need them to be versioned in some kind of model repository. And Git is not a good place for this to be, because models can be pretty large, and so can the data. So we need other places to store them with some kind of stringent controls. Again, we also need some continuous integration for training and delivery. Maybe we can use some kind of DevOps tools for that. We also need infrastructure for running multiple experiments in parallel. And that can, for example, be a cloud solution of some sort. And the reason why you want to do that, again, is because you want to experiment. So you may want to be able to run multiple experiments in parallel with different kind of fine-tunings of your model. Let's say you run 10 experiments in parallel, and each experiment has its own algorithm it's trying to fit against a set of data. And then lastly, you need a way of doing model monitoring in production to make sure that things aren't working as expected. So generally, I like to group these kind of things into three categories: tracking, model registry, and then model monitoring. And you will see those three groups across many other tools out there in the market today. So what are the tools out there that are popular, that you should be aware of, and that you may want to use? Well, I think the most common one, I would say, and definitely one of the more popular ones, are Databricks MLflow. It's open source. It is, I think, part of Foundation now as well. And you have multiple different implementations of this across the different cloud providers. I think Azure has its Databricks MLflow service, and I think AWS also have that. And it's a great tool for tracking both data and metrics, as well as deploying it to production. If you look at what Azure offers natively, like a cloud service, you will look at Azure ML. Azure ML is really all about MLOps. Sure, it gives you options to do automatic machine learning and other fun stuff, but basically what it really is an MLOps service in the cloud, where you can track experiments and you can do all the fun stuff we talked about. If you want to interact with it from your training rounds, you have a Python SDK. There's also integration with Azure DevOps here, and I think there's also integration with GitHub Actions for Azure ML. It's a great service. I played around with it a bit. I haven't used it so much myself. It's a little bit expensive. The thing I would say about this is that it does not support ML models. It only supports Python and R-based machine learning models. AWS has their own IDE as well. So we have AWS SageMaker as the alternative. It's very similar to Azure ML, I think. Kubeflow is it's a very cool tool if you are into Kubernetes as a native platform. I would definitely recommend that. And then finally, we have kind of the tool that I've been working on, which is called MLOps.net. And this is, I've kind of geared this to be very focused on ML.net. So this is a native ML.net tool, but you can do a lot of similar things as you can do in the other tools if you would like to use it. So let's look at MLOps.net here a little bit more into detail and what it's all about and what you can do with it. So it's on GitHub. You can access it yourself. You can go to my GitHub and you will find it there. The reason why I created this or started working on this was actually because there was no good MLOps support for ML.net. And I've been looking at kind of getting models to production for a bit. And in the spring of last year, 2020, about a year ago, I was just trying to talk to the Azure ML PMs and understanding if we can do ML.net in Azure ML. I was playing around with MLflow and understanding if I can deploy ML.net models to production through MLflow. And I was unsuccessful because ML.net is just not standard, I would say, in the data science community. And even though it's growing as a library and it's getting very popular, it's just not kind of worth their time, I guess, to make it compatible. So what I wanted to do was create an alternative for developers to use. And what I did was creating a NuGet package as well as a .NET Global tool. So currently what the tool supports is experiment tracking. So you can track your runs and experiments. You can track your metrics, so the accuracy of a model. You can track some things like hyperparameters. You can do data tracking of schema distributions. But more importantly, you can have a model repository, so you can track version models and register models. And you can deploy automatically to Kubernetes if you want to. You can build your own image, or you can deploy it to URI that the consuming applications can call. And this is a cross-cloud supported tool, so you can have all these things hosted in Azure or AWS or Google's cloud itself. It's very kind of flexible in that sense. What we're hoping to get done in the future here, and I will definitely appreciate support from the community if you're interested, is creating a web client to manage all this, as well as adding support for data drift monitoring and automatic triggers for retraining, and also extended CLI support. All right, so with about 10 minutes or so spared before we go into questions, I want to switch over from the slides now, and I want to dive into showing you the tool and what it can do and how you can use it. And if you have any questions before that, let me know and I'll be happy to answer them. And let me switch over here. All right, so MLOps.net is right here, and I will paste this into the chat if you kind of want to follow along here in the demo and look at the tool as well. So it is a tool like many others, and we have released 1.3.1 in NuGet right now. And I tried to give an explanation here of what you can do and how you can use it. But basically what you can do with this tool is that you can use it with multiple different providers. So you can use it with Azure Blob Storage for a model repository, AWS S3 buckets, or you can use it locally in a file share. For model deployments, you can do the same thing here as well. You can do it in Azure Blob Storage or AWS 3, but you can also do it containerized in a Kubernetes cluster. So what I want to show you today is how we do it. How do we train a model and deploy it to a container in Kubernetes in 4 minutes at most? So what I have here, my end goal here is that I have a Kubernetes service in Azure. It's called MLOps.net, and it is currently very empty. But I want a Docker container to be published to this cluster here. And in that container, I want it to be an ASP.NET Core web app with one API endpoint that takes a payload of JSON and gives me back a prediction. And the use case we're trying to solve here is Titanic. So I'm trying to predict here very simply if a person will survive Titanic or not. So we have this simple CSV set here. We have passenger ID, we have survived, the passenger class, and some other information about the specific passenger. So we can see here 0 is died and 1 is survived. And depending on the person here, you can then, we can send some data to a client here and see if they survive. So for example, the idea is that we can send, we're in the 3rd passenger class and we are a male and our age is 4 years old. Will we survive or will we die? That is what we're trying to do here, more or less, with this model. So this is a very simple hello world scenario in many ways of making a machine learning model. So what we can do here is look at how the structure would look like to create that model. And I have, I'm going to show you actually an end-to-end test I have in the library itself here that does this, just to give you an overview of what you can do with the tool here. And I've added regions here around ML.NET specific code, just to kind of obfuscate the training of the model for you and focus more on the MLOps.NET tool here. But basically here, in the middle here, I'm training my model and I'm building my pipeline. So you can see I'm taking in the age and other kind of columns here for my model. And over here, what I'm doing is actually fitting my model here to getting the trained model itself. But that's not really important for us. What I want to focus on instead is the actual MLOps part here. But while we go through that, let me run the test here. Actually, let me stop the test because I want to debug the test. Otherwise, I won't get a breakpoint, which I wanted to show you something. Of course, it's going to take a little while here. 1 second, let's see if I can pause this. I'll put some breakpoints here, just to see if I can catch it before it goes too far. We'll see. Okay, I can't catch it because it's, of course, running. So let me instead go ahead and stop this. Stop. Great. All right, so let me rerun this. Let me clean up anything that was came here real quick. Okay, good. Let me do that. Okay, let me debug this now. So what are we doing here? Well, the first thing we're doing here is we're creating an experiment, and the experiment is called Titanic, because that, again, is the model we're trying to create here. So we're creating an experiment called Titanic, and under that experiment called Titanic, we are then going to have different runs. So we're creating an independent run here for Titanic. That run is going to have different set of information, an ID, and when it was run, and so forth. And let me move on here while that's working. And then what we can do here is we have to register the schema, and we can look into that a little later. But when we train the model here as part of this, we will get things like hyperparameters that we want to log. And the hyperparameters that we want to log are things like the algorithm we used and training parameters that are necessary to get the specific model. And we can just pass them straight into the tool here, and they will log them, in this case, in a SQLite database in the background. So we can actually query them later and see how this model compares to another model. And you can, of course, save this in a Cosmos DB model or a SQL Server instead. All that is configurable in ML.NET, MLOps.NET. What we then do here is that once the model has been trained and we have our specific model available for us there, which is going to be a zip file, we can then upload our model to a repository of our choosing. And this is generally going to be a blob storage in Azure or your local files here. And once you have the model, we call it a run artifact here, you can then register that. So if you like the model you train, you can register it. And registering the model will cause it to get a specific version. So you'll see here that this model here has a specific version of number 5 here for the specific experiment. And you get some other information about the specific model in itself. You can then create a deployment target. So think about this as like a test, staging, production targets. Of course, you would do this separately if you could. But you can create a test target here. So we'll say, okay, we want to test environments. We'll create a deployment target here for test. And we can see how many deployments we are given there. And then we can do things like deploying it to Kubernetes. So this line of code here is all we need to do to deploy it to this cluster here. We pass in the registered model and we pass in the deployment target. And what it will do for us, it will deploy to production or deploy that to this specific target. And once it's done, it will return a URI here with the API call that I need to make. So if I copy this one right here, put it in Postman, and remove some stuff here, and then if I pass in this payload here that is expecting and send it, I should be able to get a prediction back here. And there we go. So my predicted label is false, which means that I would not survive the Titanic in this specific instance. But if I do female and try again, it's still false. Let's do 20-year first class, see if that changes anything. True. Okay, so if I was 20-year-old female in the first class, I would definitely survive, which makes sense because I have the most likely on the lifeboats first. So you can see here, if you look at Kubernetes now, if you refresh here, we've actually gotten a new namespace here called Titanic Test. So it's the experiment dash the deployment target that is matched here. And in this Titanic Test here, I'm not sure if we have that, but we should have. I'm not exactly sure how to look at that through Azure, but we should actually have a container in here that is running that is responding to my specific calls here. So this may look simple in many ways. I hope it looks simple, at least when it comes to deploying to Kubernetes. But actually what's happening under the surface here in this code here is that we're doing multiple things here. So we are actually doing things like we are creating a new ASP.NET Core web app through through .NET New templates. We are copying things over, creating an endpoint dynamically. We are looking at your model that you train, what dependency it needs, and we're storing those in the database. We're building a Docker image for you locally. We are pushing that image to container registry if you're choosing. We are then going even further and deploying that model to Kubernetes by creating a namespace and just doing other stuff like fixing your YAML deployment files and so forth. And eventually it's going to fetch an external IP address for you and save that in the database. So you always know where your model is and what data it has, where it came from. And hopefully that is made simple by just having one line of code here to deploy it to Kubernetes. And if you want to deploy it to URI, it's also like a one-line change here to get that to working. All right. Well, with that was kind of all I wanted to show you today in terms of MLOps and a tool. But I'll be more than happy to kind of stay on the line today and answer some questions. But I would like to thank you all for listening in today, and I hope it was helpful or you learned something new. And I will always appreciate feedback on the presentation. So thank you all. Any questions? Go ahead.
I was looking at your life cycle. What additional steps would you basically add on your life cycle? So you should basically back up your results and your weights on your algorithm. Should your provider not be available for you to continue a business? I mean, the algorithms are actually the standard algorithms, but obviously I would think they would give you different results if they were running in Microsoft or AWS. So you would have to be continuously testing them in different frameworks. Should you go down and basically reroute your business to a different to use a different provider for your machines?
Yeah, sure. So
then,
I think.
Yeah, and then how would you basically save? What format would you save your your historical your weights, your intelligence, which you can reuse down the road? So if, for instance, you wanted to basically take a look at it at home, and you didn't want to use any of the fancy features which are basically on these frameworks?
Sure, I think that's a great question. So I think first of all, I assume your question with the first part is if you use Azure ML, right, or AWS SageMaker to train your models. Is that what you're trying to say?
Yeah, and then
Yeah.
suddenly like if you stored the data in say something like Aura or or Redshift,
Yeah.
and suddenly you don't have access to that data, and you think, oh, maybe I should have stored that data in a different format or something, so I could basically read it somewhere else, which doesn't have those those fancy database or warehouses.
Yeah. When it comes to the data, I think that's still an ongoing discussion. If you think about training data for your models, right? Is that what you're asking more specifically?
No, I'm just like backing up,
Okay.
because yeah, go ahead.
Yeah, it depends. When I talk about like data, like what algorithm you used, what hyperparameters you used, that is kind of I was personally would definitely go more towards like that's you figure out. You're definitely on the money, right? If you use Azure ML, if you use AWS SageMaker, you are in their hands in many ways. They are going to be the ones that hopefully I'm not losing you all. They're going to be the ones that owns the data in some ways. You own it, but it's difficult for you to get it out. If you use something like MLflow from Databricks, or if you use the tool I've written as well, you own the data because you decide where it's going to go. You just kind of define which database to use here. So for example, if you look at MLOps.net here, you actually define everything for you. So for example, right now you say use a local file model repository. So it's going to go on my C drive, use a SQLite and so forth. But you can easily use a SQL Server here instead to get things running. And I was going to show you, see if I can start this container.
But if you're using the pipeline for Microsoft, you're actually using their servers as well, then, aren't you?
Exactly.
So you're bound that way as well.
Exactly. Yeah. Exactly. That's the point, right? So if you're using Microsoft, you're going to use their services. So you're kind of tied a little bit to what you can do there. I was trying to start a SQL Server on the side to show the structure, but yes, if you're using a cloud provider, you are definitely going to be tied to their data structures, and getting the data out to move it to another provider is going to be tricky and not very easy. So you're tied there. So I would definitely.
Would that be an extra step somewhere down the road for on your life cycle, which you would have to be for availability purposes?
It could for sure.
Because like you don't know what's going to happen down the road,
Yeah, of course. Yeah, definitely. That's a good point. Definitely something to think about for sure. What was your second question again?
The format which you would actually save it so that you could reuse it, let's say on your own desktop, if you were to run your own algorithms.
Sure. I think depending on if you're looking at the model format, is that what you're asking?
Yeah, I mean, I guess you could save I guess stuff like that could be saved as JSON as a matrix, but I mean, stuff would be basically compressed in some way in the big frameworks. I'm just thinking of like how would you basically from what the format it would be saved to basically converting it to a readable form, which you could basically start taking samples of it down and running on your own machine.
So the models will definitely be stored in the same format as they're generated. So for the Python community, you will have like a pickle model for scikit-learn. For MLnet, there will be a zip file. For TensorFlow, there will be a specific format as well. So they won't necessarily be compressed, I think, in any means, at least not the ones I've seen at least. They're going to be stored in whatever model they're trained. If you want something that's cross-platform that you can use, you would like to look at Onyx models, I would say. They can be consumed and read by any framework by itself.
All right. Okay. I'm good. Thanks.
Cool. Thanks. Any other questions out there? We have one here. How do you deal with the fact that easy to use ML services are changing constantly the training data, algorithms, parameters? What happens behind the API point is total black box. Consumers, is MLOps impossible after you're 100% rolling your own? I wouldn't say it's impossible. It depends really. So ML services, like Azure Cognitive Services, right, is already pre-trained models. So you won't need MLOps for them as much as you would with other models, because you won't retrain them. They're just going to be consumed by your application. But if you think about things like the Azure ML service instead, that's very different. But MLOps in itself, that's a good point actually. MLOps for itself is really only used for your custom machine learning models that you build yourself, that you own. And you need a way to structure that process for training them and for governing them. So I hope that answers your question there. Hopefully so. If not, please elaborate on that one.
Yeah, that sort of gets at my question. I was thinking more about your earlier comment, like you don't want to get sued, so you want to be able to sort of document what happened. And well, maybe when I ran the model, or our organization ran the model 6 months ago, it gave this result. Now I go back to hit the endpoint, now it gives something else. And now how do we document and have the replicability if we're using third-party services?
That's a great point and a really interesting viewpoint. I actually haven't thought of that when you use like off-the-shelf services like Azure Cognitive Services from an explainable AI perspective. That is, I wouldn't use MLOps in that sense because it doesn't really make much sense. But you definitely have that continuously, I guess, you need to think about on making sure that the model doesn't change too much, because as you said, like they will be retrained, the behavior will change very rapidly, and you can't necessarily rely on it behaving the same throughout months. That's a good point. All right. Any final questions? If not, thank you very much for joining in today again. I really appreciate that. I hope it was useful, and I hope you have a fantastic rest of the day, guys.